So in this video, I am going to give a demonstration of a formalization or digitalization of a concept or part of physics. And the thing that I'm going to do in this video, or the concept I'm going to formalize, is the two-state canonical ensemble. And I'm going to follow these lecture notes here, and these are by David Tong. So remind you what Lean is. Lean is an interactive theorem prover. And that means you can write down definitions, like mathematical definitions and theorems, in such a way that the computer checks for you if things are correct or not. It basically does this thing called type checking, which checks to make sure what you're writing is mathematically bona fide. So we're going to formalize the two-state system in a canonical ensemble. The basics of a canonical ensemble have already been formalized into PhysLean. So one of the great advantages of using a repository like PhysLean and contributing to it is that you don't have to do anything. Again, everything that's in the project you can use in your own proofs and your own definitions. So let's try and show some results about the two-state canonical ensemble. So this is PhysLean here, and I'm using Visual Studios. I'm going to move myself down slightly. So the first thing we want to do is we want to make a file corresponding to that to the two-state system, to the system we want to formalize. So let's call it two-state.lean. And with all of these files, we want to start with a documentation, or sorry, a copyright notice, basically saying that the code is released on Apache 2, and this is necessary for it to be accepted into PhysLean, basically because that is the license that PhysLean corresponds to. So if you're making your own file here, you would put your name instead of my name, both in the copyright and in the author's place. And then we want to import the necessary files. I tend to just import like a fairly generic file to start off with. So given we're going to be using canonical ensembles, let's import the file that contains all of the stuff about canonical ensembles, statistical mechanics, canonical ensemble, basic. You'll notice that I'm using GitHub Copilot here. This is this thing where it's trying to put stuff in for me. That's useful in some cases. Sometimes it gets the wrong thing. So if I suddenly like insert a bunch of text, that's probably because I've used GitHub Copilot. So the first thing we want to do is write a documentation string or a module documentation string. So this basically tells people what the module is about. So the module is going to be about the two-state canonical ensemble. So this module contains the definitions and properties related to the two-state canonical ensemble. And I think I spelled ensemble wrong there. And we can fill this in later with more detail, but that's probably a good start. It tells people what's in the file. The next thing we want to do is we want to open the relevant namespace. So given we're going to be working in canonical ensembles, let's open the canonical ensemble namespace. Maybe this should really be like statistical mechanics starts canonical ensemble. We can change that later if need be. And so yeah, what is a canonical ensemble? A canonical ensemble is a system that's connected to a heat bath at constant temperature. So let's go actually to the definition. So it's a heat bath connected to a reservoir of constant temperature in thermal equilibrium with that reservoir. And basically the input data of canonical ensemble are the microstates and the energies of those microstates. So in Lean, currently this is the definition of a canonical ensemble. You could probably make this a lot better. This is like in PhysLean we're willing to refactor. So if there's a better definition of this, we'll change it if it becomes practical. So the canonical ensemble currently is defined with this type iota and the map from iota to R. So what's the physical meaning of this? Iota is the states, the microstates of the system. And this map iota to R is the map taking a microstate to its energy. And we can see that down here that the microstates, this is just an abbreviation, is the type iota. and the energy of a microstate is just the underlying map of the canonical ensemble. So the first thing we need to do is we need to define a canonical ensemble corresponding to a two-state system with one state of energy E and the other state of energy 0. So we're going to set one of the states to have energy 0 and the other state to have energy E. This is what David Tong does in his notes. So let me go down to the relevant section. So he says, okay, he's called the energies 0 and epsilon. I've called them 0 and E. But you could make this more general if you wanted to. You could do, they have different energies, and that would be a good refactorization of this file. And once we've done it, someone can come along and make it more general. But let's stick to this simple case for now, because this is easy to work with. So we want to define, let's call it two-state. And what are the properties? I mean, so it's already done a pretty good job, GitHub Copilot, of doing this for us. So it has an energy E, which is a real number, and it gives us a canonical ensemble, which is based on the type fin2. And that is saying, so fin2 is basically the types 0 and 1. And this is what we want for a two-state system. We have two states, so we want a type of two elements. And the first number, this is probably not the best way of doing this. So we want to go function I. So this takes the ith microstate, and we want to say if it's 0, we want to map it to 0, and if it's 1, we want to map it to E. And I have probably done my notation wrong. So yeah, this is just shorthand to say the microstate which corresponds to 0 in fin2, so I can hover over it and say 0 in fin2 gets mapped to energy 0, and the microstate which corresponds to 1 in fin2 gets mapped to E. So let's see what we can prove with respect to this canonical ensemble. So the first thing we can prove is that the partition function of this is equal to this thing here. So let's go lemma, two-state partition function. And we want an energy E. And we also want a temperature. And we want to show that, so GitHub Copilot does quite a bit of the work for us, but it doesn't quite show exactly what we want to show, because we want to show that the partition function of this system is equal to this thing here. Okay, so let's say, well, let's do an intermediate lemma, which I think is actually what GitHub Copilot wanted to do, which is two-state partition function equal to 1 add exp. So this is saying that this partition function is equal to 1 plus the exp, so the exponential of, just making sure GitHub Copilot has done the right thing here. Let me bring over here to see what I'm looking for. Trying to find the partition function which I've lost. Here we go, down here. So I want to show it's equal to this thing here. So this is equal to minus beta times by t, or beta E. So this beta, I have to open temperature, and I have to open real as well. And this beta is the inverse temperature. So it takes a function of temperature, and it gives you the inverse temperature. And this is done with respect to the Boltzmann constant. And then we want to finish, well, we don't want to finish the thing. We just want to put by sorry to stop there being any errors for now. So what does this say? Okay, so this is a lemma, and this is a lemma that says we have an input, which is the energy E, a temperature, which is temperature T, and the partition function is equal to 1 add this exponential term here. So this is our theorem or our lemma, anything after this dot by this by thing is our proof. And you can see the thing that we want to prove up here. And this is what's called our tactic state. So this is our goal, and these are our temperatures and our energies. So we want to try and prove this result. And I think the first thing we should try and do is simplify it. So let's simplify with the partition function. And that gives us this thing here. Okay, so that's actually done quite a lot of work for us let's see exactly what it's done. So it's unfolded the partition function. It's done something with negatives. It's let me move myself. It's summed over. It's turned a sum into just an addition because we're only summing over two things, and it's done something with things which we don't really need to worry about. So this simplification really took the thing we had to prove to be this, and it turned it into this thing here. Okay, so this looks pretty good right now, and you can probably see from this that the thing that's probably holding us back is this two-state thing. So actually, let's add two states to this as well. And that's actually proof the goal. So that was pretty simple. So you can see it's proof the goal because it's gone, it's given us an error saying there's no goals to be shown. And we can do that. And now we get this double tick as well. It says, you prove that goal. And this is like a formal proof. So all this proof is really doing is it's creating a term of this type. And the term is this horrible thing here. But you never really have to look at that. But yeah, this is basically what this proof here is doing. Okay, so that's good. We've proved our first thing about the two-state system for a canonical ensemble. We've shown that its partition function is equal to 1 plus its exponential. But this isn't what I started to do with it. This is not what I started to do with this partition function. What I wanted to do was show that it's equal to this cosh thing here. So let me try and prove that now. Okay, so let me create a new lemma, which is going to be two-state partition function equal cosh. And we're going to take the same inputs. And again, we're going to do this thing here. So GitHub Copilot tried to fill it in for us. This is not quite correct because what we really want is this thing here. Times by E over 2 times by cosh beta E over t. Okay, so this is now what we want to show. So the first thing we want to do is, because the really good thing about Lean is that you can use stuff you've already shown to show new stuff. So we want to rewrite the left-hand side using this two partition function lemma. And that means we now have to show this thing here. And now we need to simplify this cosh thing. So the way that I would usually do this is I'll come over to the internet, I'll go into Google, and I would type, for example, well, we want real.cosh. So we want results related to real.cosh. And we'll see all of the results that have this real.cosh in it, and we'll see what we get. Good. So this is the thing we want here. We want to rewrite this cosh in terms of exponentials, and this is just lemma. So we can come over here, we can rewrite that. In fact, let's be nicer and let's put this here. And you'll see that our goal now has simplified, or maybe not simplified, but has changed into this thing here. Let's use a hammer. Let's do simp, see where that takes us. Didn't really help us. So let's add to the simp database, mul add, because that will hopefully take this multiplication over this addition. Did that help us? No, it didn't. Okay, so let me try rewrite mul add. This is not working. So what I'm trying to do here is distribute this addition here distribute this multiplication here over this addition. And I just realized why it's not working. It's because of this 2. So if I go field simp, hopefully that gets rid of that 2. It does. And now we can do simp add. And that changes our result to this thing here. And let's also use the fact, so we now have this and this, and let's use real.exp and add, but let's do it on the left and see where that takes us. Okay, that didn't help. Okay, so what I'm trying to do now is basically take these exponentials and combine them with one another. And the reason that it's not letting me do this exponential thing here is basically this lemma here is saying that the exponential of x plus y is equal to the multiplication of those two things, and I want it to use the sympathy of direction. It's not letting us do this because of distributivity. This is 2 times by this exponential times by this thing here. So let's see if we add mul assoc to this. Good, and that's got us this thing here. And we do field simp, which simplifies it to this. And then hopefully, if I do simp add mul, and then mul commutative. Okay, so simp add mul basically distributes this multiplication of 2 over this thing here, and then it realizes you've got 2 on both sides here and cancels them, and that gives us this thing here. And then this is probably, we can just do exact question mark and it can find out how to prove this. Good. Good, so that's proved this thing about cosh, that the partition function of a 2-state system is equal to cosh times by this exponential. So let's see what else we can prove. Let's show that the mean energy is equal to, well, so this is actually asking for the case where you now have n particles, and that would involve adding two, like multiplying this canonical ensemble by itself n times, which we don't necessarily have to do. I mean, that is implemented into PhysLean, but the API around that sort of like multiplicating a canonical ensemble by itself hasn't been fully developed yet, but will hopefully be soon. So we're going to just keep n equal to 1 here, and we're going to show that the mean energy is equal to this thing here. So let's go lemma 2-state mean energy is equal to. So we want to show that this is equal to, let's get rid of the other stuff that GitHub Copilot put in. So we want to show that this is equal to E over 2 times by 1 minus tan h times by this thing here, or as a function of this thing here. And let's make this look nice. So we now want to show this is true. Okay, so we could either use, let's see, if we do rewrite question mark, let's see what we have at our disposal. Okay, so let's see, let's go to the mean energy, and we've got some results. We've got that the mean energy is equal to the log derivative of the partition function. So we could use that result if we wanted to. I think that was going to be harder than, you know, showing this explicitly by multiplying things out, but let's see what things we have, what sort of results we have with respect to this log deriv thing. Yes, so let's see. Really, we want something that's like deriv cosh. So let's see if let's see if we got anything with respect to cosh. We don't. Let's see if we've got anything with deriv and cosh. Okay, so we've got that this thing here is true. So this might work actually. So we can go. Yeah, let's see if we can go like this. We can go rewrite the mean energy in terms of the derivative of the partition function. And then we can use that we have the partition function. Ooh, okay. So this is where it gets a bit tricky because this partition function here, is the partition function as a function of beta because we're taking the derivative here as a function of beta, whereas this partition function here is just a partition function as a function of temperature. So what we want to do is we want to show that two-state partition function beta is equal to this thing here, and where beta is a real number now. So basically the proof should be exactly the same as we've got before. You could probably do a cleverer way of doing this, where you relate the partition function as a function of beta, the partition function as a function of temperature. So there's currently one way that works, which is that the partition function as a function of temperature is related to the partition function as a function of beta with the correct beta. The inverse way hasn't been done yet. So, I mean, that should be easy to do, but this should just be easy enough to prove anyway. So let's simplify with this real.cosh. And I think the rest of the proof should just be exactly the same. And it's not quite because of this. Good. Okay, so we actually want to show this thing here. So we now want to rewrite this partition function as a function of beta as this. And the reason that it's not working is y. The reason this isn't working is that this is this function applied to a specific beta, whilst we want it to be general. So let's rewrite this like this. And this is just taking this function, and then if you do this function exponentiality and you do beta, you get back to the result that we had. And this is now a statement about the functions, not the functions applied to specific things. So I'm going to keep that lemma the same and actually rename these slightly and put apply there to indicate that these are the applied versions of these lemmas. Good. Okay, so now that rewrite has worked and we get this thing here. So how do we do this now? So let us simplify log deriv. And that has given us this expression here. And this looks quite a mess, but we'll see that really there is this thing here, which is the derivative, and then there is this thing here, which is the multiplication. So if I go field simp, let's see how much field simp knows. Good, field simp knows a lot. It knows that cosh is not equal to 0. It knows that the exponential is not equal to 0. So that does a lot of simplification for us. And now we can focus on this derivative. So derivatives are a bit of a pain to work with. So let's see if we've got anything related to derivative and multiplication. This should work here. So this should bring out this 2. So we can go rewrite. That did not work. Let's try e-rewrite. That didn't work either. Okay, what I'm going to do also now is simplify things a bit by let's focus just on this derivative. So let's write a little half lemma. And what do we want to show? We want to show that this is equal to 2 times by what? So it is going to be minus beta, no, minus e over 2 times by this thing. So that's when using the chain rule when you've done derivative on the exponential. Plus, I understand there's a bunch of errors happening here, but let's see how far we go with this. Plus 2 times by e over 2 times by, let's just put exp. Oh, actually, I need t dot beta here rather than dot beta. Times by what? So it's going to be this and then this thing here. Okay, so I think that is true. So this first term is derivative on the exponential, and the second term is derivative on the cosh, and the derivative of cosh is sinh. I can never say those words properly. Hopefully I'm not missing a minus sign. We'll find out if I'm missing a minus sign because we won't be able to prove it. But let's see how far we can go proving this result. So let's see what rewrite we can get. Okay, so that doesn't really help. So let's go back to Google, which is, my place to go when it comes to this sort of stuff. And let's see if there is anything else related to multiplication. So there is this thing here, which is basically the chain rule, I believe. So we can try that. And that works good. So that's a step in the right direction. And what does that give us? So that did that split the this multiplication into a derivative of cosh and a derivative of 2 times by the exponential. So hopefully we should actually now be able to use this result that I was using earlier, which was this result here. And then we can, so that should take this 2. So if you look what this has done, is moved this 2 here. So the 2 has gone from inside to outside. And if I go simp now, let's see how much that takes us. That doesn't give us very much. Okay, so we probably want something like rewrite deriv exponential. That doesn't exist. So let's come to here and let's see what do we have which relates the derivative to the real exponential. There is this thing here, which is probably what we want. And I think that's what I tried. So it is not possible to, two possible interpretations. Okay, good. So that's easy to solve. We just give it the root one. And that has done our derivative. And if we go simp, so before I did simp, we had this derivative here, which is just a linear derivative of this beta. So if I do simp, that simplifies everything down nicely. And now we want to do this derivative of this cosh. So let's see, let's come back. I know I looked at this before, but we want to do derivative and we also want cosh. So it looks like we want this thing here. And I think that's what I typed. So let's see why this isn't working. Unknown identifier. Okay, so then we need to come here and we need to look, okay, what do I need to import? I need to import this thing here. And I might need to restart the file. No, I didn't. Two possible ambiguous interpretations. So let's do root. I'm not entirely sure why it's doing that. But then we get this thing here. So that's done derivative of cosh. And then we've got this derivative of this linear function here. So we do simp. And now we have an algebraic expression, which we now have to solve. So how do we do this? Let's just try field set. Did that work? Somewhat. Let's try ring. Okay, now that did work, but now we have a bunch of differentiability conditions, and this is because this, so if we come up here, all of these results here, you know, they have these hypotheses that things are differentiable, and we haven't shown them, so we need to show them. But really, luckily, there's a nice tactic that's really good at solving these sorts of stuff, and this is called fun prop. So that should have, so if I come here, I've now got two goals, you see. I've got this goal here, and I've also have to show that this is differentiable. So hopefully I just need to add these fun props here. Oh, I missed. Okay, that one didn't work, so let's come back to that one. That did work. That did work. Okay, so I should have one goal left, which is this goal here. And where did this come from? So I have to show that this is differentiable. Does fun prop work? Prop work? It does work. I don't know why. Why did that not let me do this? Okay. Okay, good. So these fun props are basically just telling me that these things are actually differentiable, which lets you perform these functions. So I can now, you know, take this little result that I proved, and we can now substitute it into this goal with rewrite h1, and we now get this thing here. And let's see, really the thing we now have, so we have these things on the left-hand side with cosh and sinh, and on the right-hand side, we've got this thing with cosh. Really, we want to simplify this sinh. So let's see what results we have with, sorry, not the sinh, the tan h, let me just call it. I'm not going to try and pronounce it properly. So let's see what results we have with this. I think this is the one we want. So we go rewrite this. And that replaces our tan h with sin h over cosh. Field simp should hopefully bring that cosh up. And then, if we're lucky, ring should do a lot of the work for us. Let's see what we now have to prove. So, on the left-hand side, we have this cosh squared, this cosh times by sinh, and let me go back to the notes that with the result that we're trying to prove. So we now have to think how to simplify this thing here. And at the moment, I can't see an obvious way of doing this. So we'll have to think a bit. So we want to show that this expression is true. So probably the easiest thing to do here is actually just expand everything in terms of exponentials, and then just, this is kind of like a brute force way of doing it, but if we expand everything in terms of exponentials, that should hopefully make it a lot easier. So this rewrites the sinh in exponentials, so let's do the same with cosh. Okay, and now everything is written in terms of exponentials, and we can field simp, and we get this beautiful expression here, which again is, let's do ring. Ring did it. Perfect. I was going to say this looks really complicated, and I think we're going to have to do a lot of work, but there you go. See, a lot of these tactics do a lot of the work for you. Let's see if I can get rid of this. Does that still work? It does. Good. Okay. It's always good to see what tactics ended up being useless or irrelevant. So actually that field simp ended up being quite good. Maybe we can put those there. Good. So simplifying the goal a bit. And we can, yeah, so let's replace these simps with a list of the actual lemmas they use. This is kind of good practice to kind of keep things nice and clean and make things run a bit quicker instead of simp having to search through the whole database of results. So, okay, what have we shown? We've shown that the partition function of the canonical ensemble is equal to this cosh thing here. We had to do a little bit of work to do the partition function as a function of the inverse temperature rather than just a function of the temperature. And then we showed that the mean energy of this partition function is equal to this e over 2 times by 1 minus tang. So I think I'm going to stop there. There's probably a bunch of other things you can try and prove with this. For example, what is the entropy of the two-body system? But I kind of want to finish by showing you how you would, contribute this to the project. So I'm currently working on a clone of PhysLean, and I have write access to the PhysLean project, which if you want to make a pull request, you just message me on the Sulip or message someone on the Sulip, we give you write access. So what we do is we create a branch. Typically we call this like feature. What is it? It's two-state. The two-state canonical ensemble. And I'll bring my changes and I'm going to do feature two-state properties of the two-state canonical ensemble. And let's commit those. Let's publish this branch. So before this gets accepted onto GitHub, it's going to have to pass some linting checks. So you can run these locally by running leg execute lint all, and that should do some of the linting checks. Well, one of them that I've actually missed, which it's definitely going to pull up, is I need to add the file that we created to this PhysLean file. So, and this has to be done in alphabetical order. So we want to add, just below this, we want to add two-state like that. And let me actually cancel this because I think it's going to pull up that error anyway. And let's see what it does. Hopefully this shouldn't pull up too many errors. But yeah, this will give you like the sorts of checks that you need to do that GitHub will put on it to make sure that it's like the style is correct and all of those sorts of stuff. So I'm going to move myself up a bit because I can create a new one and I can also run simultaneously the other lint, which is scripts.lint_style.sh. And we can see that it didn't pull up any errors. There's a lot of junk here, but none of these are errors. These are kind of like files which are the outputs which are not related to the program. This leak execute all is taking a long time, probably because it's going to build a project. So I'm gonna stop here. But yeah, so this kind of shows how you would formalize something related to canonical ensemble into PhysLean. Let me add this linting that we did to this, and then I can press, I'm on a Mac, I can press Command R and I can make a pull request to the project. So I can create this pull request and then hopefully it will get merged. I mean, it will get merged eventually after it's passed all of the linters. And yeah, so that's kind of like how you would formalize the canonical two-state system, canonical ensemble two-state system into Lean. Hopefully that was interesting. Hopefully it was useful. Let me know if you have any questions. There's the Lean Sulip, where there is a PhysLean channel. You have to search for it. But that's where most of the discussions related to the project happened.